Okay, so today I will continue focusing on working out the universality of quantum computing. So, and I will revisit the first part from the last lecture again, where we had trouble with an entry in the matrix, and also the number of gates that we were counting at the end. I realized later that they are proportional to d square and not just d. So we'll go through that. But before this, I want to give you a hint about thinking about question number 2 of homework that is due, I think, tomorrow now. Let me start sharing my screen. Okay, so I think figured out a way to show you my cursor. Let's see if it works today or not. So I go to Spotlight and let's see if, oh, not this. Okay, so first let's discuss the hint about Q2. So you're supposed to show that Hadamard can be implemented with a construction like this. And you have to come up with matrices A, B, and C. Okay, this X is Xk. So the best way to think about this is actually thinking on the block sphere. So we know that the Hadamard gate is a 90-degree rotation on block sphere. So if you have a state like this, the Hadamard gate transforms this rotation to by 90-degree to along to this x-axis if we start at the z-axis around y-axis. So Hadamard gate is a 90-degree rotation around y-axis. And if you want to think about now these ABCs, what you know that this x is a 180-degree rotation, this x is a 180-degree rotation, and then you have to figure out this A, B, and C so that the total rotation is 90-degree when all of these are implemented. But you also have to keep in mind that at the end, the net rotations given by A, B, and C should be 360 degrees, because if you get a rotation of 360 degrees by A, B, and C, that will fulfill the criteria that the A, B, C is identity. Because when these X gates are not operating, we want to have an identity operation, because I want you to implement controlled Hadamard. And when these X's are on, we want to have this A, X, B, X, C as a 90-degree rotation. So if you think in terms of these rotations, then you can come up with these ABCs that are required for this problem. Okay. Heather, is this okay?
सर इसमें हमने बस अज्यूम कर लेना है, यानी कि फिजिकली ब्लॉक स्फीयर पे रोटेशंस करके देख लें कि हम किस तरह से लैंड करते हैं यहाँ पे.
अज्यूम क्या करना है?
यानी कि हम उसको बस मेंटली तौर पे रोटेशंस को वहाँ पे इम्प्लीमेंट करके ब्लॉक स्फीयर पे, तो उस हिसाब से हम गेस करके इसमें एबीसी बनाएंगे.
जी जी, there's no I would say a methodical way of coming up with ABCs for any of the games.
क्योंकि मैं उनकी मैट्रिक्स वगैरह बना के जनरल केस में और उसको मल्टीप्लाई करके देख रहा था. और आपने सर लास्ट जो फर्स्ट लेक्चर था उसके अंदर आपने कहा था कि इफ यू वांट टू इम्प्लीमेंट यूनिटरी ऑपरेशन यूजिंग द रोटेशन गेट्स, तो उसके लिए आपने फिर हमें एक एक्सप्रेशन भी बताए थे ए, बी और सी के लिए, जनरल एक्सप्रेशंस.
जी जी,
मैंने वो यूज करके भी उनकी जो प्रॉपर कैलकुलेशन थी उससे भी ट्राई किया था, तो इन द एंड कोई आंसर नहीं निकल रहा था प्रॉपर.
वो दैट्स a different construction in the sense that then you will have to relate those rotation matrices to ABCs via the relations given in that section. You remember there, if I go to that, so there's a particular relation that A is equal to RZ of beta RY of gamma by 2. Similarly, B and C are defined. Yes, you can come that way, but then you will have to start first seeing how to express Hadamard using these three rotations. And then from these rotation matrices, you can compute A, B, and C given in corollary 4.2.
ठीक। अच्छा सर, अगर हमारा पास कोई यूनिटरी ऑपरेटर है, उसको हमने तीन जो मैट्रिसेस हैं उसके हिसाब से लिखा हुआ है, लेट्स से एबीसी हमने कोई बना लिया, तो इफ वी जस्ट पुट एक्स किड्स इन बिटवीन दैट, तो वो उसका आइडेंटिटी हो जाएगा, उसका ऑपरेशन, यानी कि ऑपरेशन नलिफाई हो जाएगा सिर्फ
नहीं,
बीच में एक्स रखने से?
नहीं, ऐसा नहीं होगा।
यानी अगर मैं यहाँ पर एच को इम्प्लीमेंट कर लेता हूँ, अगर आर एक्स आर वाई आर एक्स आर जी और आर एक्स से, तो अगर इसको मैंने फिर इस फॉर्म में लिखना है ए एक्स बी एक्स सी में, तो उस तरह इसमें कन्वर्ट किस तरह करूंगा उसको फिर?
आप जो, हाँ, if you have found these rotation matrices, then there is a straightforward way given in Crowley 4.2. This A matrix is obtained from RZ RY like this, and then there's an expression for B and C as well.
यस, और ये कहाँ पे लिखा हुआ है उसको, यानी कि ए एक्स बी एक्स प्लस सी में कैसे करेंगे?
So as soon as ये देखें ना, ये A का एक्सप्रेशन RZ RY से आ गया ना, इसी तरह B जो है उसका एक्सप्रेशन भी है RY माइनस गामा बाय 2
अच्छा अच्छा,
RZ.
ठीक।
सो ये सब्स्टिट्यूशंस गिवन है कि ABC कैसे फाइंड करने हैं।
सही है, ठीक है। अच्छा सर, ये मैंने आपके लेक्चर से देखी थी ये सब्स्टिट्यूशन, तो ये बुक में कहाँ पे गिवन है? ये हमारी बुक में है या फिर कहीं और पे है?
हाँ नहीं, आप ये नेल्सन चोंग में ही है, सेक्शन 4.2।
चलिए ठीक है, सही है, देखिए। थैंक यू सर।
ओके, और अगर आप इंट्यूटिवली कंस्ट्रक्ट करना चाहते हैं तो देन यू कैन थिंक अबाउट रोटेशंस लाइक दिस, बट मैथमेटिकली यू कैन कम दिस वे. सो you work out these RX, these rotation matrices, and then from there you can find ABCs.
ऑलराइट, ठीक है। अच्छा सर, जो पहला क्वेश्चन था उसके अंदर भी हमने उसको, जो जनरल स्टेट थी उसके ऊपर आर वाई तो एक्ट करवा दिया था, लेकिन उसको हम एक्सप्लेन किस तरह करेंगे ये वाई एक्सिस के अबाउट ही रोटेट हुआ है? क्योंकि वो एक बहुत कॉम्प्लेक्स एक एक्सप्रेशन बन रहा था, जिसमें एक कैट जीरो का एक कंपोनेंट बन रहा है कोफिशिएंट, और एक साथ फिर कैट वन का भी एक बन रहा है कोफिशिएंट।
जी जी, उसका एक तरीका ये हो सकता है कि आपको करने की जरूरत नहीं है, लेकिन अगर आप रिग्रेसली देखना चाहते हैं तो आप जो परपेंडिकुलर प्लेन है ना, अगर आप वाई एक्सिस के राउंड कर रहे हैं, तो अगर आप उस वेक्टर का प्रोजेक्शन फाइंड करें एक्स सी प्लेन में, और फिर प्रोजेक्शन जो है उसका एंगल फाइंड करें किसी भी एक्सिस से उस प्लेन में, यू विल सी दैट द एंगल ऑफ द प्रोजेक्शन चेंजेस बाय द गिवन अमाउंट. लेकिन अगर आप उसको ऑपरेट करें एंड you can show it for a couple of examples that it does rotate by the given angle alpha, then it's okay with me.
ओह ओके, ठीक है, सही है, थैंक यू।
आप जनरल अप्लाई करके तो कोई स्पेसिफिक स्टेट्स ले लें और उनको देखें कि लेट्स से जीरो स्टेट है, वो एंगल अल्फा से रोटेट हो रही है एटसेट्रा, दो तीन स्टेट से शो कर दें तो दैट्स गुड इनफ.
चलो उस तरह हो जाएगा, ठीक है, वरना फिर मैं सोच रहा था कि उसको इक्वेशन की फॉर्म में किस तरह शो करेंगे रोटेशन को।
हाँ, क्योंकि वो देखें वो
ट्राई
3D
कर
में
लेंगे।
है ना, तो वो जो इन जनरल जो थीटा और फाई है दोनों एक कॉम्बिनेशन से चेंज होते हैं, और टू शो द रोटेशन बाय एंगल अल्फा अराउंड अ पर्टिकुलर एक्सिस, द rigorous way is that you take the projection in a plane perpendicular to that axis and see by how much the projection rotate. और projection की जो rotation है वो आराम से, चूंकि वो एक 2D plane के अंदर है, वो हम equation से देख सकते हैं.
सर मैं इस आसान को मैं इसके बारे में इस तरह सोच रहा था कि अगर हमने दिखाना है कि तो अगर हम एक्स वाई जी कोऑर्डिनेट्स ड्रॉ करें बॉक्स में, तो वाई राइट साइड पे जा रहे हैं, तो मैंने ये सोचा था कि जब वो रोटेट कर रहा होगा व्हाटएवर दैट स्टेट इज, तो उसकी वाई वैल्यू कांस्टेंट रहेगी, या उसका कौन सा एंगल है y एक्सिस है वो भी कांस्टेंट रहेगा। तो अगर हम इन दोनों में से कोई भी चीज़ प्रूव कर दें तो हम वो इट वुड बी इक्विवेलेंट टू प्रूविंग के वो सिर्फ y एक्सिस के लॉन्ग रोटेशन है, करेक्ट?
ठीक है, ठीक है।
तो अगर y की वैल्यू नहीं चेंज हुई तो वुड यू सजेस्ट कि हम कार्टेशियन में कन्वर्ट करके इस तरह करें, या वो गलत, मुझे वो इतना
मेरे
आइडियल तरीका नहीं है?
as far as the homework is concerned, अगर आप उसको जनरल स्टेट पे अप्लाई करके उसके बाद 2-4 एग्जांपल्स के लिए कन्विंस कर दें कि यू नो इट्स डूइंग व्हाट वी आर सेइंग इट्स डूइंग, देन दैट्स फाइन। रिगरसली जो है, देयर आर कपल ऑफ वेज टू डू दैट एंड मे बी वन इज व्हाट यू आर सेइंग।
ओके सर।
ओके, अच्छा एक चीज तो ये बताइए, ये कर्सर मूव होता हुआ नजर आ रहा है आपको कि नहीं?
सर मूव करेंगे, अभी तो नहीं नजर आ रहा।
अच्छा ठीक है, अभी नहीं कर रहा। अच्छा लेट मी।
सर आई वाज वंडरिंग कि ऊपर ये जो हैंड साइन बना हुआ है इसका काम, ये अभी आया था पॉइंटर, ये अभी आपने कुछ किया था तो आ गया था पॉइंटर, लेजर पॉइंटर आया था।
हाँ नहीं, अभी आ जाता है, देख अब नहीं आ रहा।
नहीं अब नहीं आ रहा।
अब नहीं आ रही सर।
ठीक है, अभी आ जाता है, वो मुझे पता चल गया कहाँ से आ रहा था। जैसे ये आ रहा है, ये एनोटेट का एक बटन है और उसमें ये स्पॉटलाइट है। तो अच्छा, ये लेजर पॉइंटर तो बना हुआ है, लेकिन ये अच्छा ये माउस के साथ अब मूव होता हुआ
यस
नजर आ
सर,
रहा है।
यस सर, यस सर, यस सर।
ठीक है, ये माउस के साथ ना मूव होता है। तो वो जो मेरे पास हाथ में पेन है ना, उससे नहीं मूव हो रहा।
सर पिछले सेमेस्टर मेरे ख्याल से आप इसी तरह करते थे, वो पॉइंटर के साथ हो जाता था मूव आपके, वो पेंसिल के साथ।
अब देखें, अब ये
अब
पेन नजर आ रहा है
पेन
मूव।
पेन मूव हो रहा है जी।
अच्छा अच्छा ठीक है, अब जो ये मैं लिख भी लेता हूँ इससे, ये मूव भी कर रहा है। चलें, लेट्स सी, अगर आप अभी काम कर दे तो गुड।
बट सर अगर ये एनोटेशन वाला है तो ये जब आप पेज स्क्रॉल अप करेंगे तो जो इसकी राइटिंग है वो स्क्रीन पे ही रहती है।
हाँ ठीक है। अच्छा नहीं है, बाकी वो भी एक मसला है, सही कह रहे हैं।
हम सर ये जो यहाँ पे एक हैंड का सिंबल बना हुआ है उसके साथ कोई ट्रैक भी है वन नोट के ऊपर ही, इससे हो जाएगा शायद, इसे
हाँ,
ट्राई करें।
सर जो
ये
हम पहले
मार्कर्स के
जर्नल
साथ है।
माइक्रोसॉफ्ट जर्नल जो यूज करते थे वो अच्छा नहीं है?
वो ना कभी कभी क्रैश हो जाता था।
सर वो
तो
अगर आप थोड़े थोड़े टाइम के बाद सेव करते हैं ना कंट्रोल एस से, तो वो क्रैश नहीं होता।
ठीक है। अच्छा चलें, मैं कोशिश करता हूँ, अदरवाइज देन वी कैन गो बैक टू दैट। असल में आई लाइक दैट इवन बेटर, क्योंकि उसमें जो नोट्स हैं वो पेजेस हैं वो भी A4 साइज के होते हैं। तो लेट्स सी इफ वी कैन गो टू दैट। ओके, सो यहाँ पे ये मूव होता नजर आता है।
अभी नहीं आ रहा सर।
हम
अभी
सर
कुछ
आपकी वो
नहीं
स्क्रीन
हुआ।
ही शेयर वो नहीं हुई, आपकी जो शेयर हुई थी।
Let me share this one. ठीक है, so let's begin. Okay, so इसमें ये कर्सर नजर आ रहा है।
जी
सर
सर,
लेकिन बहुत छोटा है, इसको बड़ा कर सकते हैं
ये
कर्सर को?
वो फॉन्ट साइज सर अगर
हम्म।
जो थिकनेस है पेन का।
जी जी ठीक है।
अब ठीक है सर।
ठीक है। Okay, so let me save it somewhere. Okay, so let's begin this thing. इसमें let me start again from beginning, and I'll quickly review what we were trying to do yesterday. So हम ये कह रहे थे कि we have a general unitary U, okay, and this is a D by D matrix, and in general, you know, all entries are general entries, except subject to this condition that u dagger u is equal to u dagger identity, that this u is a unitary. Okay, and subject to this thing, we were trying to show that we can express any unitary as a product of two-level unitaries, and two-level unitaries are matrices that are identity matrices, except that at four positions in those matrices, there are non-zero and non-unitary elements. But of course, these still remain unitary matrices. And to show this, we started with a three-level, with a 3x3 matrix, because using a similar scheme, we can show that we can reduce any matrix using that technique. Okay, so let me start with that. So we had this A, B, C, D, E, F, G, H, E. And again, this is a unitary matrix that U dagger, U dagger, U is identity. So we said, okay, the trick is to come up with matrices that make the elements at, let's say, this location and this location 0. So for that, suppose B is 0 already. If B is 0 already, what we can do, we can take a unitary matrix U1, which is actually an identity. Okay, because it will do nothing. But if B is not 0, then we can see that we can come up with a unitary matrix U1 like this, that if I have an entry here, which is B, and an entry here, which is minus A, and 0 here, because this middle row, when this will multiply with the first column, we'll see that we'll get a 0 at this position, because this B into A is BA, and then minus A into B is minus B. And then when we add them, we'll get a 0. But to make sure that this is a two-level and unitary matrix, we have to
U1 नहीं समझ आए. U1 identity क्यों है?
अगर B वैसे 0 है तो then of course we are saying
अच्छा,
that we do nothing
सही
and
सही.
B is already 0.
ठीक है ठीक है ठीक है.
And if B is not 0, then I'm trying to make B 0. ठीक है?
ठीक है सर.
तो अब जो middle row है अगर वो ऐसी है, तो to keep it a unitary matrix, I will have to have a top row like this, that let's say this is an A star and this is B star, so that this U1 U dagger is identity, but actually we need more than that. I will have to divide this thing with some number, let's say M, where M is A mod square plus B mod square. Okay, so that it's so unitary matrix, have this thing that the eigenvalues have an absolute value of 1. So to sort of normalize it, I'm dividing this number with this thing, because all of the rows have to be normalized. When I add A mod square plus B mod square, I should get 1. To make sure, so I'm dividing with M. Now this is a matrix that when you multiply this U1 with U, we'll get something like this. So A star A plus B star B plus 0. So A star A is A mod square, B star B is B mod square, and divided by A mod square, B mod square. This is essentially a number M square by M. Okay, and then I will have some element here, let me call it some prime, and some element here, let me call it prime, and this is 0, and this is E prime, F prime, H prime, I prime, and there is some C prime. Is that okay with everyone? Okay, the key to note is this, that this is a real number, the number over here, because of the way these elements work. So this was a mod square plus b mod square divided by a real number. So this is ultimately a real number. Okay, now to make this c prime 0, we and again I can do, okay, if c prime is 0, I can take another matrix unitary, which is identity. But if c prime is not 0, then I'll have to come up with a matrix U2 such that I can make this 0. And to make it 0, again, I will have to have a matrix like this. Let's say, so I'm calling this number still some a prime, but remembering that this is a real number. Anyway, so let's say I have a prime star 0, c prime star 1 0 0, c prime star 0 minus a prime star. And again, I'm dividing with some number n, where n is a prime square plus c prime square square root, so that, you know, all rows are normalized. Now, if I multiply with this last row with this first column, this element, the element corresponding to this will become 0. And let's see what do I get at this point. So here I have a prime and there's a c prime. So a prime mod, a prime star and c prime star. So u2 into u1u will be again some number n square over n, and then I will have 0 here, and suppose something over here is a, b, c, d double prime, e double prime, f, g, h, I. Is everyone okay now? And again, let's call it some a double prime. And we have to remember that this is a real number. Now let's see, because since these three are unitary matrices, this matrix, let me call it some V, this also has to be a unitary matrix. So if this has to be a unitary matrix, it means V dagger V has to be an identity. And V dagger is a double prime star, D double prime star, G double prime star.
पहली term really?
कोई बात नहीं, I'm just writing it for the sake of argument.
ठीक है, ठीक है.
0 and then E double prime star, H double prime star 0, F double prime star, and I double prime star into this V. Now, when I multiply the first row with this first column, I get a mod square, because this first row into this first column only, there's a prime into a prime mod square. And then this first row with the second column will give me d prime e prime star plus g prime h prime star, and similarly I will get something here. It would be d prime h prime and g prime f double prime. So g prime into this h. So last one, okay, sorry, I double prime. Now, when the second row gets multiplied with the first column, I get d double prime, e double prime, h double prime, g double prime, H double prime, G double prime. There are stars as well. Anyway, so when the third row multiplies the first column, I get D double prime, F double prime plus I double prime and G, and there are something over here. Now, the first thing that we see is this thing, that this has to be an identity matrix. It means A mod square has to be equal to 1. And since we already know that A mod square has to be 1 and it's a real number, so there is only one possibility, and that is that A double prime is actually has to be 1. So essentially, when we multiply with this U2, there is no other way than for this A double prime to come out to be 1. Okay?
आंसर किस तरह कह रहे हैं हम कि उसको 1 ही होना चाहिए?
क्योंकि ये जो प्रोडक्ट है ये आइडेंटिटी के बराबर होना चाहिए, तो आइडेंटिटी होने के लिए ये जो एलिमेंट है ये 1 होना चाहिए।
अच्छा हाँ ठीक है, सही है।
अब in the same mean this has to be 0 and this has to be 0. Okay, and we also know that since all rows have to be, you know, equal to, they all have to be normalized. So now there's only one possibility, and that is that D double prime and G double prime also has to be 0. And that double 0 will also make sure that this entry and this entry is 0 and this entry and this entry is 0. Because if D double prime, G double prime are 0, then all of these are zeros, because if they're not 0, then we'll have to make E double prime, H double prime, and I and F double prime 0, which will essentially make the whole matrix 0. So it means that this is 1, and if this is 1, then this has to be 0, this has to be 0, so that the row is normalized. And that means that we have now a structure for U2, U1, U, which is like this. There are some A, B, C, D, E, F, H, I. And then the third element, U3, can be, you know, just the conjugate transpose of this part, 1, 0, 0, 0, 0, star, H star, sorry, this is F because I have to transpose them to make sure that this is the inverse of this, and I conjugate. So when we multiply with U3, we get U3, U2, U1, U identity, which means that U can be written as U1 dagger, U2 dagger, U3 dagger. And since U1, U2 are unitary, their daggers are also unitary, and they're all 2 levels. So we have broken down this U into some matrix U1, U, let me call it V, V1, V2, V3. Okay. All right, so let's now see if what happens if we have a general D level unitary matrix. So if we have a D by D matrix, it means that we can express it as a D minus 1 level, you know, unitary, and we will have to have D minus 1 gates, D number of gates. Because you saw over here that why it's not converting, that this U was a 3 level 3 by 3 matrix, so we needed 3 unitaries to reduce its dimension by 1. Now here, if it is a D level matrix, we need D unitaries to reduce their dimension by 1. So we need, D gates, and then for each of these D gates, we need D-1 gates, D-1 unitaries. And then for each of these, D-1s, we need D-2, and so on. So at the end, we will have total number of unitaries, which are, let me write the total number of gates. D-1, and then D-2, all the way to 1. And if you add all of these, this is just a series like 1 plus 2 plus all the way to D-1. But let me add D and minus D. Then this sum is nothing but D into D plus 1 by 2 minus D. So this is D into D-1 over 2. So the number of gates are of the order of D square. I can forget, this part, because this is the leading term. So the total number of gates that we need to break down a general D-level unitary to a combination of 2-level unitaries, we need D square gates of the order of D square gates.
सर जो बुक में ये लिखा हुआ था उसमें ना उसमें इनइक्वालिटी का साइन था, तो मुझे वो समझ नहीं आई कि वो इनइक्वालिटी क्यों कह रहे हैं कि दैट नंबर शुड बी लेस देन और इक्वल टू डी, यानी कि जो ब्रैकेट हमारे ऊपर टर्म है d into d-1 over 2.
Let me check.
सर वो जो D-1 D-2 की मोटिवेशन थी वो आप दोबारा एक दफा रिपीट कर सकते हैं?
जी. सो जो पहला क्वेश्चन था कि वो इनइक्वालिटी क्यों है, तो दिस इज द मोस्ट नंबर ऑफ गेट्स, बिकॉज समटाइम इट कैन हैपन दैट आवर U can already have some zeros at some places, and we don't need a unitary for that. For example, when we were over here, if the C prime is already 0, so it means U2 is an identity, so U2 is not needed. So this is the maximum number of gates that we have to have in order for it to reduce to 2-level unitaries. In general, the number of gates would be either equal to this or less than this. Okay?
जी सर, ठीक है, आगे समझ. थैंक यू.
Okay, so let's count the number of gates again. So we have this D by D matrix reduced to these D matrices, and so actually it's better if I do it in another way, in a numerical way. So if we have 3 by 3 matrices, I need 3 gates. If we have 4 by 4, what we first need 3 matrices to, let's say this is A, B, C, D. So I first need 3 unitaries to make these B, C, D 0. So I need these 3 unitaries for this. And then after this, we will get how many gates? We will have a unitary for these 2 elements, because then I will get a 3 by 3 structure over here. So to convert this 3 by 3 structure to 2 by 2 structure, I will need 2 more unitaries. And then at the end, so this is like 3 by, and then at the end, I will have this, 2 by 2 unitary left here. So I will need 1 gate to invert this. So for a 4 by 4 system, I need 1 plus 2 plus 3 gates. Subhan, is it clear?
Yes, sir. It makes sense.
Okay, so if I have a 5-level matrix, then first I will need 4 unitaries to reduce these 4 elements to 0, then 3, then 2, then 1.
ठीक है sir. Yes, समझ आ गया.
Okay. All right. So, okay. So, any question regarding this construction? Perfect. So, let's now go to the next part, which is how to implement this 2-level unitary, each of the 2-level unitary that we have got. All right. So, the second part is how to implement a general 2-level unitary. First of all, you have to remember that our general 2-level unitary, let's say we have a 1 here, 1 here, 1 here, 1 here, 1 here, and maybe there is some element here, some here, some here, and maybe some here, but everything else is 0. This is not a single qubit gate. Okay, so you need to have this thing in absolutely clear in your mind, that a 2-level unitary is not a single qubit gate. It is still an n-qubit gate, because we are doing something jointly on all of the inputs, on all of the qubits. The difference, however, between a general unitary and a general n-bit unitary and this 2-level n-bit unitary is this, that this 2-level unitary only acts non-trivially on 2 computational basis states. So if we have n-bit system, so for n bits, our computational basis states are 2 power n. Okay, and if I just write them explicitly, so there is this 0, 0, 0 state, then 0, 0, 0, 1 state, and so on. So a general unitary would non-trivially a general unitary can non-trivially act on each of these computational basis state, but a 2-level unitary only act non-trivially on 2 of these basis states.
And just थोड़ा सा repeat कर सकते हैं, थोड़ा सा connection का मसला था, तो मैं थोड़ा समझ नहीं इनसे क्या बात है.
Let me take an example. So suppose we have an 8x8 unitary like this. I have a here 0, 0 all the way to 0, then 0, 1, 0. B here 1, 0, D here. So A, B, so a C here. So if you see this, unitary, this only non-trivially acts on a computational basis state, which has a 1 at the top and 1 at the bottom, if I write it in matrix form. Okay, so either you operate it on this state or this state. Every other state will be like an identity for this one. Everybody is okay with this?
सर एक स्टेट वही तो हो सकती है कि जिसमें पहले वाला भी 1 हो एंड वाला भी 1 हो.
वो तो इन्हीं की सुपरपोजिशन ही होगी ना. I'm just talking about the basis state.
ठीक है.
Yes sir, वो सिर्फ इन्हीं स्टेट्स पे अप्लाई करेगा. सही बात है.
So everyone else will have a 1 somewhere else, and then it's an identity. So this is the difference between a general unitary and a 2-level unitary. So let's now see how we can implement this 2-level unitary. This 2-level unitary can be implemented in terms of multi-control X gates and in terms of multi-control single qubit unitary, which the single qubit unitary is now given by this. So I'm going to implement this in terms of a multi-control unitary, single qubit unitary and multi-control axis. And the way for that is this, that we use Gray's code. So let's say this is a computational state 0, 0, and this is a computational state 1, 1, 1. So you start with one of the computational basis state, either 0, 0 or 1, 1, 1. Yesterday I started with 0, 0, but let me start today with 1, 1, 1. So let's say I have qubits A, B, C. So I start from 1, 1, 1. Now I'll keep changing one qubit at a time. Let's say I change this thing, then I change the other one, and then I change the other one until I reach the other computational state. So I started from here, I reached at this point. And now
हम इन पे कुछ कंट्रोल कोई ऑपरेटर नहीं अप्लाई कर रहे होते थे लास्ट स्टेप के अंदर
अभी करते हैं, ये तो जस्ट मैंने सिर्फ ग्रेस कोड लिखा है ना. So the circuit is going to be given like this.
सर ये जो मेथड था इसके अंदर हमेशा हम जो दो बेसिस स्टेट्स होती हैं जो हमारा ऑपरेटर इफेक्ट कर रहा होता है 2 लेवल, खाली उनमें से एक से स्टार्ट करते हैं और बस दूसरे तक जाना होता है, या फिर 1, 1, 1 तक एंड पे या 0, 0, 0 तक एंड पे जाना होता
नहीं नहीं नहीं, जो दो स्टेट्स हैं उन्हीं से उनमें से एक से दूसरे तक जाना है, हमें हमेशा 0, 0, 0 से 1, 1 तक नहीं जाना. ठीक है
जी. हमने v टिल्डा क्या लिखा है, ये नहीं समझ नहीं कि मैट्रिक्स.
मैं अभी बताता हूँ. सो द सर्किट इज गोइंग टू बी लाइक दिस. आप पहली दो स्टेट्स देखें, उनमें देखें कौन सी क्यूबिट्स का सेम स्टेट है. सो बी एंड सी हैव द सेम स्टेट and the state is 1, 1. So I have A, B, C. So and this A qubit is different. So I apply an X gate on A controlled by B and C. Then I look at the next two states and see what is same and what is different. So A and C are same, and A is 0, 0 and C is 1, 1, but B is different. So now I apply an X gate on B. It is controlled by A and C such that A control is with respect to 0 and C control is with respect to 1 until I reach the last pair. When we have reached the last pair, we are not going to apply a control X, but we will apply a control U controlled by the qubits that are in the same state on the qubit which is in the different state. So I apply this single qubit unitary defined by this and controlled by the other two qubits.
हमसे लेकिन तो हम पहले सबसे पहले हमने A को चेंज किया ना, ये भी तो अगर हम पहले B को चेंज करें C को चेंज करें तो it shouldn't make a difference, right?
It doesn't make a difference.
तो इन पे कंट्रोल किसी एक पे भी अप्लाई कर दें तो
बिल्कुल
सही है, सही है.
So last time हमने जो सर्किट बनाया था वो इससे डिफरेंट था.
Yes,
but it was doing exactly the same thing.
Yes, sir.
Anyway, so this is this, and then after this part, you just reverse these whatever has been done before this. So it was this gate, so I apply this gate, and then it was this, and then like this. And it can be shown very easily that this circuit actually implements this unitary. And actually, let me show it quickly. Using control axis and a single qubit unitary. This U tilde is the single qubit unitary that if we use in this circuit, the whole circuit implements this n-qubit unitary. And let's see how. अगर आप इस जनरल
फिर से समझा सकते हैं U tilde क्या कह रहे हैं?
U tilde जो है ना, ये वो सिंगल क्यूबिट यूनिटरी है जिसकी मदद से हम इस n क्यूबिट यूनिटरी को अप्लाई कर रहे हैं. ठीक है,
इतना समझा दें मतलब कि कैसे होगा ये.
So let's see how it does. So for that, let me first see that if we have any state which is, let's say, does not involve this 0, 0, 0, 1, 1, 1, then what will happen for a general unitary? I will get exactly the same thing, right?
Yes, sir.
You can check, because if I operate this unitary on 0, 1, 0, I will get 0, 1, 0 back again.
Yes, sir.
Now let's see what happens to 0, 1, 0 state when it passes through this circuit. So this is 0, 1, 0. So 0, 1, 0. So when it passes through the first gate, this becomes, so this is 1, this is 0. This gate will not be applied. So it will remain 0, 1, 0. So when it comes here, so this is 0, 1, and 0. So this will not be applied. So it will remain 0, 1, 0. So when it is here 0, 1, 0, this control operation will not happen. It will remain 0, 1, 0. When it comes here again, so these two gates are the same. So nothing happens, and at the output you get 0, 1, 0 state. Okay, so similarly, you can see that any state that is not either 0, 0, 0 or 1, 1, 1 will pass through it as it is, undisturbed. And that's what it should do. Okay, so the same thing has happened that I was fearing, that it has crashed. Let's see how much is saved. Okay, luckily everything is okay. Let me start sharing again. Let's see if there's a full view. Okay, so the 0, 1, 0 state has passed through as it is. Okay, let's now see what happens if we apply this unitary on state, some state which is a combination of 0, 0, 0 plus. But for that, actually, it would be easier if I just work with one state. So if we apply it to 0, 0, then let's see what this U does. If this U acts on this 0, 0, 0 state, we get A 0, 0 all the way to B. So this is the state we get, which is A 0, 0 plus B 1, 1. So let's see if we get this A 0, 0 plus B 1, 1 if we pass this 0, 0 state through here. So here it is 0, 0, 0. Here it is, so this is 0, this is 0. Nothing happens here. So I get 0, 0, 0. When this 0, 0 passes through here, so this is 0, this is 0, nothing happened. This is still 0, 0. So when this 0, 0 comes here, this U tilde is applied. So at the end over here, I get, so this U tilde is this. So what I will get is U tilde
सर आपका पॉइंटर बहुत छोटा हो गया, इसको बड़ा कर देंगे?
हाँ मैं इसको बड़ा कर लेता हूँ, थैंक यू। So this is a little bit tricky, okay, because this U tilde is only working on the C qubit. So once it passes through this, the state would be like this: 0, tensor 0, tensor U tilde 0, because this is state of A, B, and C qubit. So this 0 is, 0 tilde tensor 0. When this U tilde works on 0, so this is A, B, C, D, and this 0 state is 1, 0. So A, B, this is what I get. So this would be 1-0 tensor, 1-0 tensor AB. And if you work it out, this is exactly A000 all the way to B. And this is exactly the same state, A000 plus B11 that we get from the general unitary. So this circuit does indeed implement the general unitary, the general two-level unitary in terms of just single qubit gate and control X gates. Okay.
Yes, sir.
Okay, now this is, part of your uh, part of your homework, where you have to count the number of single qubit gates that are required to implement an n-qubit, control X gate, and you will see that they are of the order of n. Okay, you'll have to prove there might be some constant number multiplying, dividing, but they are of the order of n. And if I count the number of gates in series, so they're also of the order of n, because if this is a 3-qubit gate, at most we can go from 000 to 111 or 111 to 000. In general, it could be less than that, because we might have a unitary which only impacts 010 and 011 state. In that case, we may not need any of this and this gate. We only need, just one control unitary. But at most, we can go from 111 to 000. So this is a 3-qubit gate, which means I can have at most n-1 gate on this side and n-1 gate on this side and one here. So I can have at most like 2n plus 1 gates. So which is of the order of n. So total number of single qubit gates. So total single qubit or control X gates, they are of the order of n square.
मुझे 2n नहीं थे.
एक n उसका भी है ना. So 2n तो है कि कितने टफोलीज लग रहे हैं, ठीक है, and each टफोली has an order of n gates in it.
अच्छा, सही.
Okay. So total gates is n into n. So n square is the number of single qubit or control X gates required to implement this one. And if I know count number of gates all the way from general unitary after breaking it down to single qubit or control X gates, my total number of gates, are, let me just put this one. They're essentially less than or equal to, but they're of the order of n square. And for how many gates did we need to break it down to this one? D square, and D was 2 power n. So actually, if I just do exactly, it was D into D minus 1 over 2, and this was D square over 2 minus D over 2. If let's just work with D square. So D square is nothing but 2 power n square. So this is like n square 4 power n number of gates. This is the upper limit on the number of gates that are required to implement a general unitary in terms of single qubit gates.
I'm really sorry sir, मैं confused हूँ. वो n square नहीं थे. अभी हमने देखे वो
n square तो है ना एक 2 लेवल के लिए, और 2 लेवल तक आने के लिए जनरल यू से कितने 2 लेवल गेट हमें चाहिए थे? हमें चाहिए थे d स्क्वायर ऑर्डर के गेट या d
जब हम एक हायर लेवल एक हायर डायमेंशनल मैट्रिक्स है वो 2 सही समझ गया.
सो
n स्क्वायर हमें सिर्फ 2 के लिए चाहिए.
जी कि a general quantum algorithm. So the most general quantum algorithm that you can think of on n qubits require for its implementation single qubit and two and control X gates, which are of the order of n square 4 power n. This is, little bit disheartening, because this tells us that we need exponentially many gates to approximate to implement a general quantum algorithm. So this essentially, disheartening, because this tells us that quantum computing is not some magic bullet that can solve any computational problem efficiently, because we see that there might be because we have just saw that in general we require exponentially many gates. So the goal of designing a quantum algorithm is to exploit any structure in your general unitary or any symmetry that you can find that can give you the number of gates that are only scale polynomially as the number of qubit increase.
सर
जी जी,
ये जो हमने डिकम्पोजिशन कर ली सिंगल क्यूबिट गेट्स में, तो ये 2 लेवल यूनिटरी को कर लिया। तो अगर हमारे पास जनरल यूनिटरी हो जिसके अंदर ये 0 एलिमेंट ना हो, सारे नॉन जीरो एलिमेंट्स हो, तो उसको डिकम्पोज किया जा सकता है।
उसी को तो हमने किया जब हम जनरल यूनिटरी लिया था हमने, तो we didn't assume any them to be zero. We worked out the number of unitary operations to make them zero.
अब अभी ये जो 8x8 मैट्रिक्स हमने लिया हुआ है, इसमें मोस्टली एलिमेंट्स जीरो थे, सिर्फ 4 एलिमेंट्स जो थे वो नॉन जीरो और बाकी 1 1 थे।
बिल्कुल, ये तो 2 लेवल है ना, ये तो जस्ट 2 लेवल है।
ऑलरेडी ये 2 लेवल यूनिटरी है, तो अगर इस तरह का हम नॉन जीरो एलिमेंट्स ले लो तो फिर हम उसको इस फॉर्म में पहले लाएंगे।
जी जी, बिल्कुल बिल्कुल। सो इफ यू स्टार्ट विद अ यूनिटरी that have elements, many elements non-zero, so first you express that in terms of 2 level unitary by using the method that we just saw over here. यहाँ पे जो method देखे इसकी मदद से, so you start with general unitary and you express them in terms of d into d minus 1 over 2 number of 2 level unitary, and then each of the 2 level unitary has to be implemented like this.
So why does it have to be implemented like this? तो हमने अपने लिए एक शॉर्टकट बनाया है, लेकिन असल में भी यही वो करना होता है।
So you can think of some other way to implement that. That's fine.
इसकी वजह से वो एक्सपोनेंशियल फैक्टर आ रहा है ना, जब इसे तोड़ते जाते हैं छोटे टू लेवल्स में, तो वो 4n।
This is actually a good comment. So maybe you can think of a general way of implementing any 2 level unitary with number of gates required less than that would be something worthwhile.
सर एक और चीज़ ये कि आप एक जनरल सिस्टम की बात कर रहे हैं, लेकिन जैसे ये सिस्टम है, ये तो जैसे अब फर्स्ट में पाइथन में काम करें, आप एक इफ कंडीशन लगाते हैं, आप एंड लगाते जाएं, तो आई मीन दिस इज ट्रू फॉर एनी सिस्टम कि जितने ज़्यादा आप एंड्स यूज़ करेंगे उतनी ज़्यादा कंपटीशन तो चाहिए होगी। तो लाइक आई कैंट थिंक ऑफ अ क्वांटम सर्किट जिसमें आपने सारी क्यूबिट्स की वजह से किसी एक क्यूबिट पे कोई ऑपरेशन परफॉर्म करना है, और हमारे इस तरह के होते भी नहीं है कि हमें सारों को यूज़ करने किसी एक क्यूबिट को की स्टेट चेंज करने के लिए। यहाँ पे तो एक जनरल सिस्टम में तो ये हो रहा है ना कि सारी क्यूबिट्स को यूज़ करोगे ABCDEFG किसी एक को चेंज करने के लिए, तो हमें तो ये करने की इतना मतलब इस तरह का सिस्टम बनाने की जरूरत वैसे ही नहीं है। डोंट यू थिंक सर?
जी, काफी सारे प्रॉब्लम में ऐसा नहीं होता, आप सही कह रहे हैं, लेकिन हम जो बात अभी कर रहे हैं, हम यहाँ पे बात कर रहे हैं असूलों की, कि आप अगर ये कह दें कि एक खास किस्म का मेरे पास यूनिटरी है, वो उसमें ये जीरो है, ये नॉन जीरो है, तो मैं तो उसको सिर्फ 5 गेट्स में इंप्लीमेंट कर सकता हूँ। तो आप कैसे कह रहे हैं जी कि इतने सारे गेट्स नहीं होंगे, हालांकि हो सकता है वो 100 क्यूबिट गेट हो। तो भाई ठीक है, उसके लिए हम तो बात कर रहे हैं कि इन जनरल के and the most complicated unitary you can think of will require this many gates.
वो तो फिर इस तरह गूगल के भी सर्वर को एक बहुत कॉम्प्लिकेटेड प्रॉब्लम दे दो, वो करोड़ों साल लगा देगा। ये तो बहुत एक्सट्रीम है ना कि बस हर क्यूबिट पे हर ऑपरेशन परफॉर्म हो रहा है। तो इससे मतलब मैं कहना ये चाह रहा हूँ कि टू से कि क्वांटम कंप्यूटिंग मैजिक बुलेट नहीं है, तो एक बहुत एक weird सी statement है इस तरह के scenario को consider करने में. I mean मुझे तो लगता है कि magic
On
है
the other
अभी.
hand, suppose I say that quantum computing is a magic bullet to solve every problem in very few gates, yeah, in polynomially many gates only. But then people
जी
will
sir.
come up with some unitary. It doesn't matter if it represents some problem or not. And there are some problems that we can think of that would require exponentially many gates. So then we will be wrong.
फिर से आपको क्या लगता है ये magic bullet है कि नहीं है?
So in general, it's not. For some
Okay.
problems, is, and that is actually the job of quantum algorithm people to find those problems that can be solved efficiently. But it's important to remember that not all problems can be solved efficiently on a quantum computer.
सर आपको क्या लगता है कि क्योंकि अभी बहुत बेसिक लेवल पे क्वांटम कंप्यूटेशन सर्किट्स होते हैं तो आपको क्या लगता है कि आफ्टर हाउ लॉन्ग would we have high level languages for quantum computation जिस तरह Python है?
Already people are building high level languages. For example, even in Qiskit, you can just call the QFT function without having to worry about QFT, and you can call subroutines to perform, let's say, molecular simulation without having
लेकिन
to.
फिर भी हम एक सर्किट के अंदर काम कर रहे थे कि अब हम वैसे नॉर्मल पाइथन है इसमें हमें सर्किट का नहीं सोचते हैं हम बस अपने वेरिएबल साथ काम कर रहे होते हैं जो भी ये सर्किटरी होती है
Even I
बैक
think
एंड पे यस सर
जो C sharp है नहीं देखिए बैक एंड पे तो सर्किट होगा ही हम तो यूजर को जो देंगे हाई लेवल लैंग्वेज उसको
एग्जैक्टली ना एग्जैक्टली लेकिन जैसे QFT वाले फंक्शन में वो भी सर्किट के अंदर ही लग रहे होते हैं तो जैसे C sharp है इस तरह की कब आपको लगता है होगा
already I think this Q sharp that is almost equivalent to C sharp and you don't have to learn quantum computing too much to implement that. And then there is I think ये Microsoft वालों की Azure software है that also is trying to implement quantum computing for people who don't know quantum algorithms.
Okay, sir.
There's a lot of work going on it, and the only thing is this, that when will it get mature? That I think will take some time. Because abhi tak people are still figuring out which technology to focus on or which one is the winning technology to implement quantum computing. So it is still something which looks promising, but it will take time.
Yes, sir. Okay, sir.
Okay, so let me see how much time we have. Okay, we have 10 minutes. So let me keep going with the last part, because now we are coming to, sort of the root of the problem. And that is that, okay, we now have broken down our problem from general unitary to two-level unitary, and then single qubit unitary, plus of course CX. Now single qubit unitary is still arbitrary. Okay, we had that ABCD matrix, right? And in general, this is the infinite number of gates still, because these ABCDs can have any value subject to that unitary requirement. Which means that if we want to implement this thing arbitrarily, either we need to have an access to a quantum computer which can implement any of this function, or we now have to think about something else, and that is that suppose our quantum computer only implements a finite set of gates. For example, let's say it implements Hadamard, and the T gate is that pi by 8 gate. And control X. So this is a fixed set of gates. Or maybe we have a quantum computer which may perhaps implement Toffoli gate and some other, and maybe some other combination and so on. But the number of gates is finite. So the question is, how can we implement this general arbitrary unitary using a finite set of gates? And the first question actually is that, can we implement this general single qubit unitary with 100% accuracy with a finite set of gates? The answer is no. And the reason is this, that if you even think about a single qubit, okay, forget about multi-qubits, just think about single qubit. So for a single qubit, we know that the state of the single qubit can be represented by a vector on a Bloch sphere. But on the Bloch sphere, there are infinite possibilities. There are infinite number of points because it's a continuum. And since it's a continuum with a discrete set of gates, we can only reach a discrete set of points after applying discrete number of gates. You apply maybe 1,000,000 times different combinations of your finite set of gates, then you can work out how many possible points you can access on the surface of the sphere. You will find out that it's a finite number of points that you can access, but the possibilities are still infinite. It means the first part is that using a discrete set of gates, we cannot implement any arbitrary state exactly.
However, pi by 8 वाला गेट कौन सा है? T गेट, ये किसने बनाया? एक क्वांटम सर्किट में इम्प्लीमेंट हुआ है ना, तो अगर हम pi by 8 का बना सकते तो हम pi by n का बना सकते हैं कि कोई भी नंबर
नहीं बना तो सकते हैं, but we don't want to do that because we need to put more and more capabilities in the hardware.
Can't we have a dynamic hardware के आप वो just उस run time के अंदर वो implement हो सके?
That that has its own problems. Think about a classical circuit. अगर आपने कभी सोचा हो,
obviously एक वो project आप बना देते तो वो change
so you are going to make a chip and sell it to someone, and if you want to implement a continuum of state, then you have to provide a lot of flexibilities, which mean that
yes.
each operation will have its own errors.
फिर इसका एक और ये तरीका है कि pi by 8 की जगह pi by 1000 या बहुत बड़ा नंबर डिनोमिनेटर में हो कि डिस्क्रीट को कंटीन्यूअस की तरफ अप्रोच कर सको, फिर वो रिजिड ही हो, उसको चेंज ना ऑन करना पड़े, लेकिन बना शुरू में वही हो.
And of course you have to think about other one. For example, you say, okay, I'll give you Hadamard pi by 1000. So if I need a rotation of 10 degrees, I will end up applying
थोड़ा मसला हो जाएगा.
That gate of the order of 1000. So there's always a trade-off that you have to think about.
Yes sir, true.
You're going to give finite number of gates. So then it doesn't actually matter that there are like 3 gates or 4 gates. We can give 1000 gates. Remember, we are right now talking about the matters of principle. That in principle, if you want to give a discrete capabilities to your hardware, then the first thing is this, that you cannot implement any state with 100% accuracy. There's always going to be an error, and this is simply because the state space is a continuum, and with the discrete set of gates, with a finite number of gates in your circuit, you can only access a finite number of points. So what we will actually do in tomorrow's lecture then, because we are getting out of time, is that we will show that, for example, for this set, I will show that this is a universal set of gates that you can implement any unitary using this approximately. But the good thing is this, that if you want to implement your state psi to a point to within, let's say, a distance of epsilon on this unit sphere, then you can do that, and you can reduce this epsilon as small as you want by paying a price in terms of number of gates.
So ये फिर से समझे, आपने तो कहा था कि pi by discrete है, तो वो वैसे नहीं आ सकेंगे जितनी मुझे दफा लगा लेना.
But if you decide, if once you decide on epsilon, let's say you say I can have my state defined up to an accuracy of 0.01. in some sense. Okay, then I can divide this sphere into circular patches of radius epsilon, and those number of patches would be finite. And with my finite number of gates, I can reach that.
लेकिन सर हमें थोड़ी देर पहले ये नहीं पता कि you will never be able to reach some spots.
Yes.
No
So
matter.
if you define your epsilon to be 0, then your
क्या
number
मसला
of
हो जाएगा? ठीक है, if epsilon is big enough, तो आप n
not big
number
enough.
of gates.
It's not 0. Other than 0, you can take any epsilon, and I can give you number of gates that
एक
will
inverse
give you within that epsilon.
inverse proportionality आ जाएगी, जितना छोटा epsilon होगा उतने gates बढ़ना शुरू हो जाएंगे हमारे,
बिल्कुल,
right? ठीक है.
So if your discrete set of gate has this capability that you can represent any state with a prescribed precision greater than 0, then your gate set is universal in this sense that you can implement any unitary up to an accuracy that you desire.
So classical computation में भी we have floating point errors. Let's say मैंने quantum bit के अंदर ना एक number store करवाना है, तो एक decimal place के बाद आगे uncertainty बढ़ना शुरू हो जाएगी. तो हमारे पास classical computation में भी floating point error आ जाता है कि आप एक decimal point के बाद
तो
आप
क्लासिकल
आगे
कंप्यूटेशन है वो जो आप ये बात कर रहे हैं, these are errors that
different
are
things.
avoidable in principle. Okay,
लेकिन वहाँ पे भी ना से वहाँ पे मसला थोड़ा सा डिफरेंट है, लेकिन सिमिलर भी है. वहाँ पे मेमोरी का मसला है, क्या इतनी मेमोरी अवेलेबल नहीं है कि आप उसे एंड तक स्टोर कर सको. इन द सेम वे हमारे पास इतने गेट्स नहीं है यहाँ पे कि आप उसको इतनी एक्यूरेसी दे सको. या मैं गलत रिलेशन बना रहा हूँ.
जो क्लासिकल कंप्यूटेशन की एरर है, they are totally of different nature. They are not errors in principle. ठीक है, they are errors that are coming from the hardware and these things. So, but in classical computation, all the number of states is discrete because you work with 0 and 1. So with a finite number of bits, there are only finite number of possible states at the end of computation, and you can reach them with a finite number of gates.
Yes sir.
सर मेरा एक क्वेश्चन है.
जी
सर हमारा जो टिफोली गेट होता है सिंपल वाला कि हमने 2 क्यूबिट से कंट्रोल किया और तीसरे क्यूबिट पे उसको अप्लाई कर दिया.
जी
सर उसको हम एज कितने नॉट गेट्स उसको आइडेंटिफाई करते हैं? वो सिंगल एक नॉट गेट है, डबल क्यूबिट से कंट्रोल्ड एक नॉट गेट?
नहीं, हम जो एक सिंगल CX है उसी को एक नॉट गेट कहते हैं. टिफोली जो है, it has I think 5 नॉट गेट्स in it.
यानी कि अगर हम 2 क्यूबिट से कंट्रोल कर रहे हैं एक क्यूबिट के ऊपर एक्शन, तो दैट आर बीइंग इम्प्लीमेंटेड बाय 5 1 से दूसरे वाले को कंट्रोल करने वाले.
बिल्कुल.
ठीक है.
उसे हमने बना के भी दिखाया था ना.
फिर असाइनमेंट मेरे ख्याल से एक क्वेश्चन था, इसमें था कि बताएं कि इसमें कितने कंट्रोल नॉट गेट्स होंगे. तो अगर हम 2 क्यूबिट्स कंट्रोल करके एक को इंप्लीमेंट करें तो विल काउंट इट एज 5 नॉट गेट्स.
बिल्कुल.
हमने क्लास में करके दिखाया था ना ये. पहले हम उसे वापस स्टेट वापस स्विच भी करते हैं. हमने टिफोली गेट नॉर्मल कंट्रोल एक्स से बनाया था पूरा.
जी.
तो टोटल पे 5 ही लग रहे थे मेरे ख्याल से.
Any other questions?
सर
जी
ये जो आज का लेक्चर है, इसकी रीडिंग नैन्सी लिन चुआंग के अलावा कोई दूसरी है रीडिंग मटेरियल?
असल में ये जो टॉपिक है ना, दोनों इस तरह से ये मैंने देखा है कि ऑलमोस्ट किसी भी और बुक में नहीं ट्रीट किए हुए. इवन के अगर आप लेक्चर नोट्स देखें जो मैंने भी अपलोड किए हुए हैं और भी लोगों के, सो पीपल जस्ट एक्चुअली रेफर टू नैन्सी लिन चुआंग फॉर दिस. सो दैट्स प्रीटी मच इट.
सर उसमें सिर्फ ये एक ही पेज में हुआ है तकरीबन?
नहीं, एक पेज नहीं, इसमें काफी लंबा टॉपिक है. अगर आप सेक्शन 4.5 देखें तो इट्स अ वेरी लॉन्ग सेक्शन, बहुत डिटेल से.
टू लेवल यूनिटरीज को जब वो करता है उस इशू के ऊपर ज्यादा वो नहीं है.
नहीं, सारा ये काफी डिटेल से है, आप उसको देखें. इट्स इन वेरी डिटेल. ओके, और कोई क्वेश्चन किसी का?
हमसे होमवर्क मैन कब तक सबमिट करवाना है हमने?
कल तक कर दें।
ठीक है सर, थैंक यू सर।